4 engines just failed. On one side, during ignition. Starship's booster was seconds from liftoff when the onboard computer caught it and shut everything down instantly. Not a slow spool down. A violent emergency cutoff. Elon Musk confirmed it minutes later. 2 Raptor engines damaged, removed, replaced. And SpaceX did it in days, not months. So how do you go from an aborted launch to a second attempt this fast? Here's exactly what happened and how they fixed it. Let's go back to that exact second. T-0. Ignition confirmed. For half a second, Starship's Super Heavy booster looked alive. Fire under the skirt, steam rolling off the pad. 33 Raptor engines, all supposed to light up in one coordinated sequence, thousandths of a second apart. And then, nothing. No liftoff. No movement. Just fire, water, and silence where a roar should have been. If you were watching the live stream, you heard the confusion in real time. That wasn't a bird. Because for a moment, nobody knew what they were looking at. Here's the detail that matters. Those 4 engines weren't scattered randomly across the engine bay. They were clustered together, all in the middle ring, all on the same side. Hold on to that. We'll come back to it. Here's the part of this story most people are going to miss. Starship didn't fail on Thursday. Its abort system worked exactly the way it was built to. Every rocket this size is covered in sensors, thousands of them, across the booster, the ship, the launch mount, and the tower. All of it feeding into one onboard computer, checking everything in real time. When 4 engines didn't confirm ignition, that computer had a fraction of a second to decide. Keep going and risk lifting off unbalanced, or shut everything down before the clamps ever released. Here's why that decision matters so much. 33 Raptor engines produce close to 16 million pounds of thrust combined. Take 4 away, all from the same side, and you don't just lose power, you lose balance. A rocket that size, fully fueled, sitting on the ground, cannot survive lopsided thrust, even for a fraction of a second. So the computer made the safe call. That's not a scandal. That's a rocket doing exactly what it's supposed to do under the worst possible pressure. But surviving the abort and walking away clean turned out to be 2 very different things. Ripping the plug out of the wall. Here's the problem nobody talks about after a successful abort headline. A normal launch scrub, called before ignition even starts, is gentle. Engines spool down step by step. Pressure bleeds off slowly. Nothing gets shocked. This was not that. This was a shutdown after ignition had already begun. Engines already spinning up, already flowing super cold propellant, already building pressure, got cut off in one abrupt stop. Think of it like yanking a running engine's power cable straight out of the wall, mid-startup, with 0 warning. For a Raptor engine, that's a rough event. The turbo pumps inside spin at tens of thousands of revolutions per minute. They don't like sudden stops. The propellant lines are under heavy pressure. They don't like sudden closures either. And this isn't the first time SpaceX has run into this exact failure mode. Booster 19, back on Flight 12, went through nearly the same scenario during a static fire test. Same forced shutdown mid-ignition. Same outcome. Engine damage, a rollback, replacement parts. So when it happened again with Booster 20 on Flight 13, the question wasn't whether anything broke, it was how much. Before we get to the fix, it helps to know what SpaceX is actually fixing. Raptor isn't a simple engine. Most rocket engines burn their fuel in one relatively straightforward pass. Raptor uses something called full-flow staged combustion, which, in plain terms, means every drop of fuel and oxygen gets pre-burned in 2 separate turbopumps before it even reaches the main combustion chamber. Why go through all that extra complexity? Because it lets the engine run hotter, more efficiently, and with far less wear than older designs. It's part of why Raptor can be reused dozens of times instead of once. But that efficiency comes at a cost. More moving parts, spinning faster, under more heat and pressure, means more places for something to go wrong during a sudden, forced shutdown. That's the trade-off sitting underneath this entire story. The same complexity that makes Raptor one of the most efficient rocket engines ever built is the same complexity that makes it sensitive to exactly the kind of violent mid-ignition abort we saw on Thursday. The verdict and the pattern, nobody's saying out loud. Within hours, SpaceX had an answer. Not 4 damaged engines. 2. The other 31 cleared inspection clean. That's a meaningful number. It tells you the shutdown likely didn't spread beyond the engines that failed to fire in the first place. The damage stayed contained. But here's the part worth sitting with. Twice now, back-to-back, a forced engine shutdown has ended in a Raptor swap before SpaceX could fly. Flight 12, a static fire abort. Flight 13, a launch abort. Is that just bad luck twice in a row? Or is Raptor 3, the newest and most compact version of this engine, still working through a specific weakness when it comes to sudden shutdowns? SpaceX hasn't called this a systemic issue in public. But 2 rapid aborts, 2 swaps, 2 flights in a row is exactly the kind of pattern engineers pay close attention to. And in a strange way, a repeatable problem is good news. It means it's traceable. It's the failures that show up once, with no clear cause, that actually keep engineers up at night. So here's the real question hanging over all of this. Is the fix simply swapping out damaged hardware? Or does Raptor 3 need an actual design change? Something that lets it survive a fast abort without taking damage at all? Because a rocket meant to fly dozens of times a year can't afford an engine swap every single time something goes wrong. It's worth being specific about why this particular flight carries more weight than a routine test. Starship 5-3, the version flying on Flight 13, isn't just a bigger Starship. It's the version SpaceX needs, working reliably to build out the next generation of Starlink satellites, the ones designed to carry far more capacity per launch than what's flying today. It's also the version tied directly to NASA's Artemis program, where a Starship-based lander is supposed to put astronauts back on the moon. None of that happens on a broken engine. Every delay to Starship's flight cadence pushes those timelines back with it, not by days, but potentially by months, because NASA and SpaceX both build their schedules around Starship actually flying on a predictable rhythm. So when SpaceX turns a 4-day fix into the new normal instead of a lucky exception, that's not just an engineering win. It's the difference between Artemis staying on schedule and slipping again. Why 4 engines, all on one side? Let's go back to that detail from earlier. 4 engines, same side, middle ring. When ignition failures hit isolated, unrelated engines, that usually points to individual problems. A faulty igniter here, a bad sensor there, random, scattered across the engine bay. Clustered failures are different. When they're confined to one physical side of the vehicle, that usually points to something shared. A propellant line feeding that section, an electrical harness running to that group, a valve or manifold sitting upstream of all 4. To be clear, SpaceX hasn't confirmed a specific root cause publicly. This part is informed speculation based on how rocket engine plumbing is typically laid out. But if 4 engines on the same side failed together, engineers are almost certainly looking at whatever system connects those 4, rather than treating it as 4 unrelated coincidences. And honestly, that's reassuring. A shared cause failure is usually easier to trace than 4 random ones. Find the one shared system, and you may have solved 4 problems with a single fix. The 96 hours that fixed a rocket. This is the part that actually earns the word solution. Thursday evening, the abort happens. Within hours, not days, SpaceX engineers are already pulling data off all 33 engines, comparing sensor logs, checking which 4 never confirmed ignition and why. Friday morning, before most people were even awake, Ship 40 is already off the pad and back inside the mega bay. Booster 20 follows right behind it, not scheduled for next week. Moved that same morning. By Friday, the call is made. 2 Raptors out, new ones in. No repeat static fire test. That last part matters more than it sounds. Skipping a static fire means SpaceX trusts its own inspection data enough to go straight to flight without burning another week, proving it to themselves first. Over the weekend, the actual swap happens. Pull the damaged engines, install the replacements, recheck the connections, re-verify the data. By Monday, July 20th, the stack is back on the pad, ready for a second launch attempt. Start to finish, 4 days, not 4 months. That's the actual solution behind this headline. Not a redesign, not a committee. A fast, disciplined process. Inspect, isolate, replace, verify, fly again. No lengthy sign-off chain. No waiting on outside contractors for replacement parts. Just one team, working through the same building where the engines were built in the first place, moving from problem to fix without ever losing momentum. Here's something worth knowing before you decide how impressive 4 days actually is. Aborting after engine ignition isn't new to spaceflight. The Space Shuttle program dealt with it more than once over the decades, engines lighting up on the pad, a fault getting caught, and the whole stack shutting down before liftoff. Each time, it worked exactly like it's supposed to. The vehicle stayed safe, nobody got hurt, and the mission got scrubbed. The difference was always what came next. For the shuttle, a pad abort like that usually meant weeks, sometimes months, of investigation before another launch attempt. Every engine got pulled by hand, inspected individually, and the whole program often paused while engineers worked through a formal review process. That's the baseline this industry grew up on. A pad abort equals a long pause. SpaceX just took that same category of event, an abort after ignition, and turned the pause into 4 days. Not because the failure was smaller, because the response was faster. Why nobody else can move this fast? Here's where this stops being just a SpaceX story and becomes an industry story. Fueling the stack, the biggest rocket ever built, takes just over 35 minutes. SLS, NASA's own moon rocket, takes 10 hours just to fuel. New Glenn takes 4. That same obsession with speed doesn't disappear when something breaks. It shows up in the recovery too. Most launch vehicles are built almost by hand, one at a time, with parts that aren't fully interchangeable. When something fails, engineers often can't just swap a part. They have to custom fit a replacement, then requalify the whole system before flying again. That process alone can eat months. Starship's engines are built more like a product line than a one-off masterpiece. Raptors are manufactured in batches, designed from day one to be pulled, replaced, and reinstalled without reinventing the process each time. That's not an accident. It's a deliberate manufacturing choice. And it's exactly what lets SpaceX go from engine failure to ready to fly in 4 days instead of 4 months. There's another piece to this that most people overlook. At Starbase, the factory building the rocket sits right next to the launch pad itself. When something needs replacing, there's no shipping delay, no waiting on parts from another state, no separate contractor to loop in. The team that builds the engines is minutes away from the team that flies them. That physical closeness alone shaves days off a process that anywhere else in this industry would involve freight schedules and separate facilities before anyone even starts the repair. If you tune into the next attempt, here's what actually tells you whether the fix worked before anyone posts an update. Watch the countdown around the 60-second mark. That's the built-in hold SpaceX uses for a final systems check, moved from 40 seconds to 60 ahead of this flight. If it pauses there and clears quickly, that's routine. If it lingers, that's worth paying attention to. Watch for the deluge system. Once that water starts flowing at full rate, it's one of the clearest signs a launch is genuinely close, because those water reserves aren't easy to refill mid-countdown. Once it's running, SpaceX is committed, and watch the engine diagram at the bottom of the stream at the moment of ignition. That's exactly where this whole story started on Thursday. 4 squares that should have lit up green and didn't. If all 33 confirm ignition together this time, that's your answer in real time, before Elon Musk or anyone else says a word. Before we call this a clean win, it's worth asking the harder question. Speed cuts both ways. Skipping a repeat static fire test saves days, but it also means SpaceX is betting entirely on inspection data instead of a live retest of the exact engines that just went through a violent shutdown. That's a calculated risk, not a guarantee. And if Raptor 3's shutdown sensitivity turns out to be a real design gap, not just bad luck twice in a row, then fixing it fast, twice without addressing the root cause, just delays the same problem to Flight 14 or Flight 15. 4 days looks great on a headline. It only actually means something if Monday's engines all fire clean. That's the honest version of this story. Not blind optimism, and not doom either. Just a simple fact. SpaceX has built a process that turns a real failure into a short pause. Whether that pause is long enough to actually fix the underlying issue, or just long enough to patch it, is exactly what Monday is going to test. The twist. What this actually reveals. So here's the twist, and it's not the one you'd expect from a headline screaming disaster. The real story of Flight 13 isn't the failure. It's that SpaceX now treats a 4-engine ignition failure as a solvable, days-long problem, not a program-threatening one. That matters more than it sounds like, because Starship's entire purpose depends on flying constantly. The next generation of Starlink. NASA's Artemis moon landings. Eventually Mars. None of that works if every hiccup costs months. It only works if SpaceX can fly often, learn fast, and fix problems faster than those problems can slow the program down. Which brings us back to the question from earlier. If Raptor 3 has now forced 2 emergency engine swaps across 2 consecutive flights, does Monday prove the fix actually holds? Or does a third incident turn this from isolated hardware issue into something bigger? A pattern SpaceX has to solve at the design level, not just the repair level. We're about to find out.